Hi, everyone. I'm Lynn Clark, and I make code cartoons. And I also work in the Emerging Technologies group at Mozilla. So that means things like WebAssembly and the Rust programming language, and Servo, which is a super fast browser rendering engine. But I'm not here to talk about those things today. I'm here to talk about Fiber. When the conference organizers asked you all what you most wanted to hear about, Fiber was far and away the #1 answer. So that's why I'm excited that I get to come here and explain Fiber to you. I assume, since it was the #1 answer, that most of you probably have an idea of what Fiber is, and Sebastian did mention it earlier. But don't worry if you don't know, because I'm going to start from the basics and explain to you exactly what it is and how it works. But before I do that, I want to show you what it does. So here's an example React app. On the left, you see React as it is today, and on the right, you see React with Fiber. Now, this is a toy application. It's not very useful in and of itself, but it is a good stand-in for more real-life applications, and I'll explain why that is later. So what does Fiber do? It improves perceived performance and responsiveness for complex React applications like this one. Now that you know what it does, I'll explain what it is. So Fiber is the new reconciliation algorithm for React. That terminology, reconciliation algorithm, that might be new to some of you, so I'll explain where that comes from. When React first came out, the killer feature was the virtual DOM. And the reason that this was the killer feature was because it made coding user interfaces so much easier. Instead of having to tell the browser how to go from the previous version of your app to the next version, you could just tell React what the next version should look like, and it would handle everything in between. It turned out that this was useful not just when working with the DOM, but also when working with other things like hardware and virtual reality and native apps. If React wanted to be able to address these use cases, though, it was going to have to factor out the part of React that figured out the changes from the previous version of your app to the next version, from the part that actually manipulated the DOM to get it there. This introduced a formal distinction between the reconciler and the renderer. Renderers are pluggable, so you can use renderers from outside, from the rest of the community, to target other host platforms besides the DOM. But there's only one core reconciliation algorithm. That's what you download with React. This is why Fiber is such a big deal. Over the past year, React's core team has been doing a ground-up rewrite of this core feature, this killer feature of React. And the end result is the Fiber reconciler. Let's go back to this demo. What is it about the Fiber reconciler that takes this kind of janky motion on the left and makes it fluid and smooth? So I want to talk a little bit about what exactly is going on in this demo. There are two different updates going on. There's one that's making the triangle narrower and wider, and there's one that is going into each dot and changing the number. And this is a good stand-in for other real-life applications because it makes very visible interactions between two different kinds of updates. There's a high-priority update and a low-priority update. Sebastian talked about this earlier in his talk, but an example of a high-priority update would be when you're typing. You need to have that immediate feedback loop when you're typing. And an example of a low-priority update would be when you have things coming in from the server, updating things like the number of likes on a comment. And this shows what happens when you combine these high-priority updates and these low-priority updates. So let's talk about the mechanics of this example. You have a triangle at the top level, and then there are more triangles. It keeps going down and down until you get to a point where you have to place a dot because you can't fit any more triangles. These updates are going to touch different parts of this tree. The update that's going narrower and wider is only going to touch the top level triangle. So it's not very computationally intensive, but it is happening frequently. It's happening every 16 milliseconds to give you that fluid motion. On the other hand, the other update is pretty computationally intensive because it has to touch every single instance in this tree. But it's only happening once per second, and if it doesn't happen immediately on every second, if it's another 100 or 200 milliseconds, you're probably not going to notice. So let's look at this chronologically. In order for these side-to-side motions to look fluid, we need 60 frames per second. We need that 16 milliseconds per frame. Now, you may think that the answer to get this is to make React itself faster. But the problem is not that this update can't fit. You're only touching one instance. It's not that it can't fit in 16 milliseconds. It's the fact that it's getting stuck behind these larger updates. And most of the time that's spent in these larger updates is actually spent in the render function and other functions that are part of the user code and not part of React itself. So making React itself faster won't make this fast enough to solve this problem. But there is a way to solve this problem, and that's by making the updates play together better. And it's not just React updates that need to play together better. It's also updates coming from the browser, so things like CSS animations, browser resizes. Those would also get trapped behind these larger updates. And that's because of the way that the browser works. I've talked about this a little bit before. When you're building a website, it's kind of like your code is the project lead on this website. Unfortunately, it only has one employee. It only has one worker that's working to build this website, and that's the main thread. So the main thread is kind of like a full-stack developer. It does DOM, JavaScript, layout. It does all of the things. And as long as it spends time doing the JavaScript update, it can't do these other things. It can't do layout. And I've said before, when you use React, how it helps with that is it knows how to work better with the main thread. It's kind of like a technical lead that knows exactly how the main thread works. And so it makes the main thread more efficient in its work. It can direct the main thread in its work by minimizing and batching DOM changes. What Fiber does is basically teach this technical lead some basic project management skills, like how to split up work and how to prioritize work. And it also gives the technical lead a watch so that it can keep track of how much time has passed. So how do these new skills come into play? How do they change the way that the reconciler works? Let's start by looking at how the existing reconciler works. And this is a diagram I've used in explaining it before. On the left, you'll see the elements. So those are the things that your component hands off during render to tell React what it should build. In the middle are the instances, which React creates as a way of managing, figuring out what the previous state was, what the next state is, and what changes it needs to make. And then the DOM nodes are what React uses to actually tell the browser what it needs to do. With the existing reconciler, this is constructed layer by layer. So React will create the element, and then the instance, and then the DOM node. Or it will update the instance and then the DOM node. And to do this, it recursively calls mount component or update component until it gets to the bottom of this tree. So if you were to record a timeline of this in your browser's DevTools, you'd actually see a graphic representation of this. You'll see a stack that has all of these recursive calls. And it just keeps going deeper. This actually shows us where the problem is too, because the main thread is getting stuck underneath all of these calls at the bottom of this call stack. But if you need it to be able to come up and check for other work, see if it needs to do other things, you need to be able to break this up. And Fiber does that. It makes it possible for the main thread to compute a little part of the tree and then come back up and check to see if it has other work to do. The way that it keeps track of where it is in the tree is through a data structure called a fiber. And that's where the Fiber reconciler gets its name from this data structure. Now, the old reconciler, it didn't have a name. So retroactively, it's been given the name the stack reconciler because it uses a stack to keep track of the same thing. This Fiber is just a plain JavaScript object. And it has a one-to-one relationship with an instance. It manages the work for an instance. So it keeps track of which instance it's for using the property state node. It also keeps track of its relationships to other fibers in the tree. It's easier to understand these relationships if we use an example. So I'm going to use this example user interface. It's a list with a button, and when you click the button, it squares the numbers in that list. This only requires a handful of components. So we have a list component, and when you call render on it, it returns an array. This may be new to you. As Tom mentioned in his keynote earlier this morning, we can now return arrays from render. So when we're building up this tree, the first fiber in the tree is the host root. And that actually corresponds to the container that you injected your React app into in the DOM. And its first child is the list. There's a relationship from the host root to the list, which is child. And then there's a relationship from the list back up to the parent, which is the return relationship. Now, these children of list actually have some more interesting relationships. The button has the same child and return relationship. But the first item, you'll notice, does not have that child relationship from the list to the item. Instead, there's a relationship from the button to the item. That's a sibling relationship. And so all of these siblings are going to point to their next sibling. That's how React's going to traverse through this layer of the tree. So those are the relationships that each fiber keeps track of: child, return, and sibling. There are some other properties that fiber keeps track of, but I want to go through an example so you can see how they all work in practice. So I'm going to go back to this example that I've used before, but I want to make things a little bit more interesting. Halfway through, the user is going to click a button that increases the font size. And this doesn't need to do anything in React, so it's just a regular JavaScript update. But it's going to require some layout calculations from the main thread. So we'll see how this changes how we build up the tree. Here's the diagram that I've used before. Because there's a lot going on in the fiber reconciler, I'm just going to show the fiber tree, building up the fiber tree. I'm not going to show the elements or the DOM nodes like I have in the past. Before we start the update, we already have the current fiber tree. This was constructed during the initial render. And React also started something called the work in progress tree and added the first fiber to that. The reason that we need a work in progress tree is that we don't want to actually make changes to the DOM while we're computing the changes in this tree. And this is different from the stack reconciler. The way that the stack reconciler works is as it's walking down the tree and changing instances, it's changing the corresponding DOM nodes. So for example, when we make the change from 2 to 4 in the instance, it's going to make that change in the DOM node from 2 to 4. Before it actually computes on the instance below it, the third instance, that should go from 3 to 9. This works if you're doing everything all at the same time, if you're doing things synchronously. But if you need to interrupt this, if you need to take a break in between those two, then the browser will say, OK, well, I need to paint, I need to do a layout, and change this from 2 to 4. But it won't have the information to change the things below that. So your UI will end up being inconsistent. To avoid this problem, Fiber introduces phases. In phase 1, the render or reconciliation phase, it just builds up this fiber tree, the work in progress tree, and figures out a list of changes from that. But it doesn't actually make those changes. It's not until it gets to the commit phase that will actually make those changes in the DOM. Phase 1, the reconcile phase, that can be interrupted. So React lets the main thread go and do other work at certain points during the reconciliation phase. But phase 2 cannot be interrupted. That commit has to happen all at once, or you would get those UI inconsistencies. So our task in phase 1 is going to be to build up this work in progress tree and figure out the changes in it. Let's start an update and see how this is filled in. So to start the update, we click the button. This calls set state. When set state is called, React will add the update to an update queue, so a list of updates on the list. And then React goes to schedule the work that's going to have to happen to make this a reality. When setState was called, the app let React know that it doesn't need to have this happen. It doesn't need to do this work immediately. React can schedule this as deferred work, so it can schedule it to happen later. And to do this, it uses a function called requestIdleCallback. This is basically like React saying to the main thread, let me know when you have some spare time and we'll do this work. For browsers that don't support requestIdleCallback, React will polyfill it. And so when the main thread has some free time, once it's done with its work, it comes back to React. And it knows how much time it has to spare. So this could be a few milliseconds, or it could be up to 50 milliseconds if there are no frames scheduled in the near future. So the main thread has come back, and we're going to start building up this work in progress tree. And we'll fill it in with a function called work loop. The work loop is what gives Fiber this appearance in the timeline. It allows React to go down, do a little bit of computation, and then come back up to let the main thread get to whatever other work it needs to do. And in order to do this, it needs to keep track of two things. It needs to keep track of the next unit of work that it needs to work on, and it also needs to keep track of the time remaining it has with the main thread. So the React and the main thread get started, and they're going to start in this first pass through the work loop. They're going to start with the host root. And they're just going to copy values over from the current version to the work in progress tree. And this included a pointer to the child of the host root, which is the list. Since there are no updates, it's just going to clone the list into the work in progress tree. And since the list had an update queue, it clones that update queue too. So the list fiber is going to be returned as the next unit of work. And React comes back up to check whether or not its deadline has expired. Because we still have some time, React will go back down and start processing the list. The list does have an update queue. It has an update that React needs to take care of. So it starts processing that update. It calls the updater function, which was passed into set state. And you may never have seen an updater function before, even though they've been supported in React for multiple years. People still often use an object and pass an object into set state. But with Fiber, you really want to use updater functions, and they might even remove this at some point. So calling the updater function gives us the new state. And the update queue is finished processing. So this fiber is then marked. It has a tag attached to it because it needs to have a change made in the DOM tree. To move any further down, we're going to need to, in this tree, to keep processing this tree, we need to know about the list's children. So React's going to set the props and the state on the list instance and call render. And then we get this array of elements back. React goes through the array of elements and sees whether or not the fibers from the current tree are the same, whether or not they can be reused. And since they can in our case, it just clones those. Then it returns the first child in this list. That's the button as the next unit of work. React comes back up to check the deadline, and I think that you're starting to see the pattern that's emerging here. So I'm going to make things a little bit more interesting. The user's going to click that button to make that font size change. This adds something, a callback, to the queue that the main thread is going to need to take care of. But it's not going to take care of it immediately. Because React still has time on its clock, it's going to stick around with React and start processing the next item, the next unit of work, which is the button. This button doesn't have any children. This is the first time we've had something in this tree that we've reached that doesn't have any children, so it's not creating any new work. So React can complete this unit of work. And that means comparing the old and the new to see whether or not there have been changes. If there were changes, it would mark it as needing changes in the DOM, but since there aren't, it doesn't. And then, since there's no children, it returns the sibling as the next unit of work. Now remember, this is the item that had the number 1 in it. So React goes back up to check the deadline, then goes back down. And this will follow the same pattern as the list. But let's say that there was a should component update on the item that says, if the number prop that's passed in is the same, I know that my div isn't going to need to change. So I might as well just return false from should component update. This means that the item will not have a tag attached to it that says it needs to have a change in the DOM. The precise details of how it works when should component update returns false are still a little in flux, so I'm not going to go into the details. I'm just going to skip ahead to where the item is completed. And it returns its sibling as the next unit of work. We go back up. We come back down. It's processed in much the same way, except this time should component update does return true. So it gets marked as having a change. It gets that tag attached to it. And its div is cloned and returned as the next unit of work. We still have a little bit more time on the clock, so we're going to process this div. The div doesn't have any children, so we can complete it. We compare the old and the new, and we see that 2 is changing to 4. So we do actually need to make a change. So we attach one of those tags. And it also gets added to a list on its parent item, a list of changes. And the reason that it got added, this is the first time we're adding one of these things to a list. Item keeps track of all of the fibers underneath it that have changes. Now there's no next unit of work that it can return. There's no child and there's no sibling. So it just calls complete on its parent. It knows its parent doesn't have any more work to process. So I mentioned that this was the first time that we added the div, or that we added anything to a list of changes. And the div was added to the list of changes on the item because it had that tag that it needed to change and also had been completed. And now we've completed item, and that also has a tag. So it's going to move itself up to, it's going to start creating this list of changes on its parent. And the way that it does it, as part of that, it merges its own list of changes into the parent's effect list. That's what these lists of changes are called. So it takes the div and puts that as the first thing in the effect list for its parent. And then it puts itself on the end of that effect list. Now that it's complete, it returns the sibling as the next unit of work. And we go back up to check the deadline. But it looks like we've run out of time. So React needs to let the main thread get back to its other duties. React still wants to finish this job, though. So it uses request idle callback to basically say to the main thread, when you're done with what you're doing, come back here and we'll finish up. The main thread goes back to its desk, takes care of the callback that's waiting for it, and this may include doing layout, as it does in our case. But notice that nothing in the content of our React app has changed, even though React knows that it's going to need to change 2 to 4 sometime in the future. It doesn't do that now. When the main thread is done with the work, it comes back to React, and they start where they left off. The last 2 units of work are finished in the same way. They get their tags, and they're added to the effect list. And that completes all of the units of work below list. So now complete can be called on list. And this means that list moves everything up into its parent's effect list and also adds itself to the end. Finally, when the list is completed, it can complete its parent, the host root. So now, React sets the work in progress tree as a pending commit. This is the end of the first phase. We've updated the work in progress tree, and we figured out a list of changes in that tree. Now it's time for phase 2, actually committing this work to the DOM. React will check its deadline, and if it has time, it would do the commit now. And if it doesn't, it'll use request idle callback again. And as soon as the main thread gets back to it, the first thing it would do is commit this pending commit. So we're starting phase 2. React will go through the effect list and make the changes to the DOM, starting with the first fiber, which is the div. So it changes 2 to 4. And then it moves on to the list, which is this div's parent. Now, for our case, there actually aren't any changes here because we aren't using refs. But if we had a ref on here, that ref would be detached now, and then it would be reattached later. And React keeps updating the DOM and going through this effect list. Now all the changes were calculated in phase 1, and they've been committed to the DOM tree. This means that the work in progress tree is actually a more up-to-date version of the state of the app than the current tree. So React needs to fix that. What it does is it switches the pointers so that the current pointer now points to the work in progress tree that we just built. And there's a nice benefit of this. It means that React can reuse the old objects. It can reuse the things in the work in progress tree and just copy over key values the next time it has to build up a work in progress tree. This is called double buffering, and it saves time on memory allocation and garbage collection. So now we're done with this commit. React goes through each of the effects in the effect list one more time and does a little bit more work. So it will do the rest of the lifecycle hooks. It will update any refs. And it will also handle those error boundaries that Tom was talking about earlier. So this is a new thing to React. It makes it possible for you to actually handle the errors in a particular part of the app. And this is good because it makes it easier for React to show you helpful error messages. But it also means that components will have a chance to handle errors themselves using a handle errors method. So once lifecycle refs and errors have been taken care of for each of these effects, we finish the commit. So this walkthrough has shown you how breaking up work into these units of work makes React more responsive to browser events. And this is a nice feature. But in and of itself, it doesn't actually fix the problem that we were talking about earlier, where React commits got caught, they got trapped behind other larger React commits or lower priority React commits, updates. And in order to solve that, we need to add a little something more, which is priority. So in the Fiber reconciler, each update will need to have a priority assigned. These are currently the priorities. Synchronous works pretty much like the stack reconciler does today. Task work needs to be handled before the next tick of the event loop. Animation uses request animation frame to schedule. It will happen so that you see it in the next frame. High priority, low priority, and off-screen priority, those are all scheduled like I was talking about, using request idle callback. High priority work should happen pretty quickly in order to seem responsive. Low priority work isn't as sensitive to these minor delays. So if you're doing something like data fetching, you're not going to notice if there's an extra 100 or 200 milliseconds in there. So low priority work can be used for that. And then off-screen is for anything that's hidden or that is off-screen currently. And it'd be nice to have it rendered in case it gets shown, but you don't need to have it right now. With these priorities, what we want to have happen is for higher priority work to jump in front of low priority work, even if the lower priority work has already been started. And again, I think looking at this in context will help you understand how these priorities work. So let's say in the last example, instead of having that font resize increase, we have an urgent React update button. The user clicks the button, and this puts a callback in the main thread's queue. But the main thread's not going to take care of it until the deadline is reached, and when it is, then it takes care of that callback, which calls set state. Then React is going to add this to the list of updates. But because it's a high priority update, it butts in the queue. It jumps ahead of the low priority update that we were already working on. And this means that when React starts work again, it doesn't start on the next unit of work that it was going to, that it was planning to. Instead, it restarts with the host root, and it basically throws away all of this work that it's done. And then React will go through the higher priority update and commit. And then it will start back over again at the beginning of that lower priority update. Now, I don't have time to get into the details of this, but I do want to answer two questions that might have popped in your head. One is about lifecycle hooks. So some of them fire during the reconciliation phase, and others fire during the render or the commit phase. That means that lifecycle methods might not fire in the same order that you expect. So in the example we just walked through with different priority updates, here's how component will update and component did update would work. First, the low priority update would fire component will update. And then the high priority update would butt in and fire component will update and component did update. And then the low priority work would get restarted and fire these two again. In some apps, there's an expectation of symmetry between these two, that they'll be called as a pair in the same order. But as you can see, that's not always true with Fiber. So to make sure that this doesn't break apps, the Fiber team is working on a graceful upgrade path for this. Another thing you might have wondered is, what if a whole bunch of high priority updates jump in line, they jump in the queue? Then your lower priority update may never happen. When this happens, it's called starvation. One way that React tries to fix this is by reusing work where it can. So if it had low priority work that was done and the high priority work didn't touch that part of the tree, then it can reuse that work. And the team is actively working on other solutions to help mitigate this starvation problem. So this is how the Fiber architecture will make React apps better in the near term. It makes updates play together better by allowing these more high priority updates to jump in line, to jump ahead of the lower priority updates. And it makes the UI more fluid and responsible. And it does this by breaking up the work into smaller units of work. These can be paused so that the main thread can get to other tasks that it needs to do. And by the way, there's a name for this. It's called cooperative scheduling. And you'll see it in other kinds of software. For example, you'll see it in operating systems to help applications play together better. And at Mozilla, we're actually currently bringing this into the browser, into the actual DOM, as a way of making Firefox more responsive with a project called Project Quantum. Beyond what cooperative scheduling does for React today, it also opens up new possibilities in React's future. So example, one of the trouble spots that Sebastian talked about this morning is startup. How long it takes to initially render the app. And you may have seen a blog post yesterday from James Kyle about this as well. The problem in many React apps is that to render a single tree, React has to fetch all of the components in a single file, and then load them, and then it starts building up the instance or the fiber tree. But this could be different. React can start building up the tree as components stream in, so that's that streaming rendering. And Fiber will make it easier to do this, and also to do it in a smarter way, as Sebastian was talking about. Another thing that Fiber could make easier is handling work in parallel. So if you add more workers than just the main thread, the work can be faster. But parallelizing things isn't always a silver bullet. There are efficient ways to parallelize things and inefficient ways to do it. Fiber will make it easier to do it in an efficient way by splitting up branches of the tree and doing branches of the tree in parallel. And this is another thing that we've experimented with successfully at Mozilla. Our new CSS style engine, which was developed as part of Servo and now is being introduced to Firefox, it handles the tree the same way. It handles parallelized sibling branches. In our testing, a page that took 130 milliseconds to render before only takes 30 milliseconds once it's parallelized like this. So you can imagine what kind of performance wins this might bring for React. Unfortunately, I don't have enough time to talk about all of these future possibilities, all of the things that Fiber could bring long term. And I wish that I did. But I think that Fiber sets React up for a few years of really interesting experimentation and performance wins. And I'm really looking forward to seeing how that turns out. So I want to say thank you to the React core team for explaining Fiber to me so that I could explain it to all of you. And thank you all for listening.